Now, we are going to go through isotropic hardening. Consider a specimen loaded with the uniaxial external load. The stress-strain curve under uniaxial external loading is shown in the figures below. If the specimen is loaded till the yield strength of the material, it accumulates the elastic strain epsilon E. At this point, if the load is removed, the specimen comes back to its original shape. Instead of removing the load, if it is loaded further, it will accumulate the plastic strain epsilon P. The total strain in the specimen is given by epsilon E, that is elastic strain, plus epsilon P, that is plastic strain. Total strain is denoted by epsilon T. Now, if the loading is removed, the deformation in the specimen will reduce by the magnitude corresponding to the elastic strain epsilon E. The deformation corresponding to the plastic strain epsilon P will still remain in the specimen. Consider that the load is still kept on the specimen. Let us assume that the specimen has an elastic strain epsilon E and the plastic strain epsilon P1. Let the stress in the specimen be Tys1. Now, if we induce additional strain equal to epsilon P2, the corresponding stress in the structure will increase from Tys1 to Tys2. This is due to a non-zero tangent modulus. In other words, additional load is required to induce subsequent plastic deformation in the structure, or the specimen hardens. This phenomenon is known as isotropic hardening. In isotropic hardening, the yield stress increases with the plastic deformation. In terms of cylindrical yield surface, the radius of the yield cylinder increases in the isotropic hardening, resulting in higher yield strength. Note that the loading considered in this case is monotonic, or increasing without reversal.